Let's explore binding energy graph and use that to understand nuclei and nuclear forces a little better. But before we start, a quick recap. What's binding energy? Well, binding energy can be thought of as the energy needed to break the nucleus apart. Break the nucleus. For example, if you take oxygen 16, 16 is the mass number, meaning total number of protons and neutrons inside of it, then its binding energy happens to be, if I just looked it up, happens to be close to 128 mega electron volt. Electron volt is a very tiny unit of energy, and mega just means 10 to the power 6. So this is the binding energy. And what does that mean? It means if I were to separate all those 16 protons and neutrons apart, I would have to supply 128 mega electron volts of energy. This much energy to break this nucleus. Another example. If I were to take, say, uranium-235, a very famous isotope used in bombs and nuclear reactors, then its binding energy happens to be 1,786 mega electron volts. So what does that mean? This means that if I have to separate all the 235 protons and neutrons of the uranium, break this uranium, it takes this much energy. So that's the meaning of binding energy. Energy needed to break the nucleus. Okay, a very quick question to you. Do you think we can use this to say that uranium is more stable compared to oxygen because it takes more energy to break uranium compared to oxygen? Can I say that? What do you think? Can you pause the video and think a little bit about this? Well, it sounds reasonable, but if you do that, oxygen is going to be very angry at you. It's going to say, hey, I only have 16 particles with me, so obviously it's easier to break me. Whereas in uranium, there are 235 particles all pulling on each other and keeping each other together. So obviously it's a bigger family, it takes more energy to break it. So that's an unfair comparison. So yeah, we can't just use this number to compare their stabilities. To compare them, we'll have to use same numbers. But how do we do that? Well, one of the ways to do that is asking the question, how much energy it takes to separate one proton or one neutron from the oxygen and from the uranium. That would be a fair comparison because we're taking equal number, 1. So let's calculate. For oxygen, to separate 16, it takes 128 mega electron volts. If I want to separate one neutron or one proton, how much energy does it take? Well, I just divide this by 16. If I do that, I've already calculated, it happens to be, turns out, about 8 mega electron volt. And these are rough numbers. So this means to separate one proton or neutron, it takes 8 mega electron volts of energy for oxygen. How much for uranium? Well, for 235, it is this much. So for 1, I have to divide this by 235. And this is why I chose these examples. If you do this calculation, it happens to be 7.6 mega electron volt. Ooh, what does that mean? That means to separate one proton or neutron from a uranium, it takes less energy compared to that of oxygen. And so who is more stable? It's the oxygen that's more stable compared to uranium. And so you see, if you want to talk about stability, you take the binding energy and divide by the mass number to calculate the binding energy per nucleon, energy required to remove one proton or neutron. And that's what we're doing here. We're looking at binding energy per nucleon of all the different elements and comparing all of them. So what does the graph look like? Well, here it is. Ta-da! So what is the graph trying to tell us? Well, it's saying that if you look at lighter nuclei, then as the number of protons and neutrons increases, as the mass number increases, notice the binding energy per nucleon, their stability basically, starts increasing. It becomes more and more stable. Then it reaches a maximum value and then slowly starts decreasing, but pretty much stays a constant. And if you're wondering at this point, which is that element which has the maximum stability, then that element turns out to be iron 56. And that means iron 56 is the most stable element in the universe because it has the maximum binding energy per nucleon. And its value happens to be somewhere close to, these are all rough numbers, okay, not exact, close to about 8.5, 8.6 mega electron volt. So the most stable element in the universe is iron 56. But now let's think a little bit more about why is it that the binding energy per nucleus, the stability increases very quickly initially, but then pretty much stays a constant. In fact, it starts decreasing, but it pretty much stays a constant. Why is it doing that? Well, it's got to do with the fact that nuclear forces are short-ranged. Okay, what does that mean? Well, let me take an example. Let me just show you a few nuclei over here. In each case, let's think about how hard it is to remove this green particle. Harder it is, more stability. Okay? Now, over here, in the first case, this green particle is only pulled by 2. But over here, the green particle is being pulled by 4 other particles. And as a result, we can say that it's harder to pull this one, so more stability. So this one has a higher binding energy per nucleon, more stability compared to the previous. And the same thing happens over here. Because there are more particles surrounding this green one, more pull, it becomes even harder now to pull out this green particle from the nucleus. So stability increases. And so this initial part of the graph makes sense now. As you increase, as you add more particles, more pull, and as a result it becomes harder to separate them, and therefore the stability increases. But what happens after a particular point? What happens over here? Shouldn't the same thing continue? Well, no. You see, it turns out that nuclear forces are short-ranged, meaning that particles can only influence or pull on their immediate neighbors. So let's see what happens from here to here. When I add those extra blue particles, they are no longer the neighbors of green particle. Right? And so these blue neighbors are just too far away from the green particles, and turns out that these blue particles, these extra blue particles, are no longer going to pull on the green particles. And so the only particles that are pulling on the green one are its immediate neighbors, pretty much the same amount as these ones. And so notice over here, it's the amount of energy required to pull this green particle apart or outside the nucleus is pretty much the same as over here, because no extra pulling force. Does that make sense? That's the meaning of short-ranged. And that's why from here to here, the binding energy pretty much stays the same. And the same story continues. From here to here, even though I've added more blue particles, they're just too far away. They're not going to influence this green particle. And so, you see, as I go heavier and heavier after a point, even though I'm adding more particles, the number of neighbors for each particle stays the same. And as a result, the energy required to remove any one particle after a point stays the same. And so because nuclear forces are short-ranged, after a point, we will find that the stability pretty much stays the same. Now, if you're really curious, you might ask, but wait, it's not a constant. The stability is decreasing. Why is that happening? Well, I don't want to get into too much complexity, but remember, there is another repulsive force at play as well. Protons and protons repel each other. And because of this repulsion, it becomes easier to pull particles apart. Now, initially over here, since the nuclear force is much stronger than the proton-proton repulsion force, the nuclear force wins out and we can completely ignore the proton-proton repulsion. But from here onwards, the nuclear force stays the same on each particle, right? But the proton-proton repulsion starts increasing because electrostatic force has no short range. It is a long-range force. And so because the repulsion starts increasing, although the attraction stays the same, the repulsion starts increasing. That's the reason why it actually makes it a little easier to start pulling your green particle apart as you go down. But you don't have to worry too much about that. But that's basically the proton-proton repulsion is the reason why the binding energy per nucleon actually decreases. But let's not worry too much about it. Let's, for our sake, it pretty much stays a constant, okay? Finally, we can use this graph to even predict what kind of nuclear reactions we can predict over here. One of the nuclear reactions is where you have a very heavy nucleus breaking into smaller nuclei. We call that nuclear fission. And this is the reaction used in nuclear bombs. Now, why does that happen? Well, let's see. Let's look at the binding energy graph. If you take a very heavy nucleus, and let's say it were to split into smaller nuclei, then these products would be towards the left side. And we can see from the binding energy graph that these end up having a higher stability compared to the reactant. And therefore, such a reaction is favored. Remember, in any reaction, whether it's chemical or whether it's nuclear reaction, Stability. Nature wants to go more towards stability, and that's where spontaneous reactions happen. And since in this reaction the reactant products are more stable compared to the reactant, this reaction is favored, and an enormous amount of energy is released, and that's what's used in atomic bombs. So this is called nuclear fission. Now, can you predict why we can't have nuclear fission for lighter elements? So if I take an element over here, which is, say, I don't know, maybe carbon or nitrogen, why can't we have fission over there? Can you look at the graph and think about it? Pause the video and think about this. All right. If you take a very light element like nitrogen or carbon, and now if that undergoes fission, if it splits, then notice the products would be even lighter, and notice they will be less stable compared to the reactant. And so this is not favored. And so this is not a spontaneous reaction. And so you don't expect lighter elements to undergo fission reaction. Does that make sense? So what happens to lighter elements? Well, lighter elements undergo fusion reaction. These elements, they tend to fuse together to form heavier elements, because now notice the heavier element is more stable compared to these lighter elements. And so you expect lighter elements to undergo fusion. And that's what's powering up our sun, or any other star for that matter, nuclear fusion. Hydrogen is combined to form helium, and later helium can get combined to form even more heavier elements, and so on. And now I'm pretty sure you can look at the graph and explain why heavier elements don't undergo fusion reaction. I'm pretty sure you can try and do that yourself.